Hey guys, Mr. Brown here, and in this PowerPoint we are going to talk about nomenclature, which is the system by which we name chemical compounds. The first type of compounds we will focus on are the simplest of ionic compounds, those ionic compounds that do not contain any transition metals nor polyatomic ions. These types of ionic compounds will simply be made of one metal element and one non-metal element. These types of compounds are relatively simple to name. All you have to do is write the name of the metal that comes first in the compound, followed by the name of the non-metal that comes next in the compound. The ending of the name of the non-metal is replaced with the IDE ending, pronounced "ide". We have some examples of these simple ionic compounds on this slide. Our first example is NaCl. The symbol Na stands for the element sodium, and the symbol Cl stands for the element chlorine. In this case, we'll change the ending of chlorine to IDE, so the name of NaCl is sodium chloride. The next example is the formula CaCl2. The symbol Ca stands for the element calcium. Cl again stands for the element chlorine, and we will change the ending of chlorine to chloride. Notice, for the ionic compounds, we do not use prefix indicators in our names. You might be tempted to call this calcium dichloride, but that is not how we name ionic compounds, because we can determine the ratio from the common charges on these ions. The next name, or the next formula, says MgF2, and Mg is the symbol for the magnesium element. F is the symbol for fluorine, which we will change to fluoride in order to complete that name. The next formula, KBr, K stands for potassium. Br stands for the element bromine, which we will alter to bromide for the correct name. The next formula says Al2O3. Al is the symbol for aluminum, and again, I will not use a prefix indicator because this is an ionic compound. O is the symbol for oxygen, and we will alter the ending of oxygen to oxide. The next formula we see is Ca3N2. Ca is again the symbol for calcium. N is the symbol for nitrogen. We will change the ending of nitrogen to nitride in order to name that ion successfully. The next formula we see there is AgCl. Ag is the symbol for silver, and Cl is the symbol for chlorine. We will alter the ending to chloride for the correct formula. Finally, we see the formula LiI. L little I is the symbol for lithium. The capital I is the symbol for iodine. We will change the ending to iodide for the correct formula. Next, we will look at naming ionic compounds with polyatomic ions. A good indication that there is a polyatomic ion involved in your ionic compound is if there are more than two elements present, and one especially is a metal, you probably have a compound with a polyatomic ion. You can use the polyatomic ion table from your text to help you answer these questions. So here we have some examples of naming ionic compounds with polyatomic ions. On the first page here, we only have examples where the anion, the negative part of the ionic compound, is the polyatomic ion. You can see in our first example here, the first element we run into is sodium. So the first name of this compound will be sodium. But then we see more than one element following it. We see CO3, so that may be our indication that it is one of our polyatomic ions. So we can look in a polyatomic ion chart and see if there is a polyatomic ion with the formula CO3. And it turns out that is what we call the carbonate ion. So the name of this species will be sodium carbonate. Our next example starts with the symbol Mg, so that will be magnesium. The next couple of elements we see is SO4. So we're going to look in our polyatomic ion chart and see if we can find an SO4 ion. Carefully looking finds that the SO4, his name is sulfate. So the name of MgSO4 is magnesium sulfate. The next example, the first symbol we have is K, which is the symbol for potassium. And the next few elements we see there is PO4. We're assuming that this is a ionic compound with polyatomic ions because it has a metal and some nonmetals. We know that there's more than one nonmetal, so we're assuming polyatomic ion. PO4 is the phosphate ion, so K3PO4 is the formula for potassium phosphate. Our next example starts with Li. That is the symbol for lithium. The next elements that come after that is SO3. Now, to be careful, because we've already seen SO4 on our polyatomic ion chart, we want to find and be sure that we're finding SO3 for this one. That is the ion sulfite. So the name of Li2SO3 is lithium sulfite. Our next examples, the first element we run into is Al, which is the symbol for aluminum. And then we see the compound or polyatomic ion NO3. And NO3 is the name of the nitrate ion. So aluminum nitrate is the name for AlNO3. Our final one is sodium. And then the OH ion is a very common ion, so you may want to commit this one to memory. OH is our hydroxide ion. So the name of NaOH is sodium hydroxide. Now do be aware there are some ionic compounds that sometimes do not contain a metal at all. Those are usually ones that contain the ammonium cation. Ammonium has the formula NH4+ and can take the place of a metal in an ionic compound. We see some examples on this slide here where we have formulas that start with NH4. So we know that's an ionic compound, and we know that it's going to start with the word ammonium. The first example we have is NH4Cl. That's the ammonium ion bonded with a chlorine ion, which we change the ending of to chloride in order to complete the real name. NH4,3P has the name ammonium phosphide. The ammonium ion is the formula NH4. The P is the symbol for phosphorus, and the phosphorus ion has the name phosphide. Again, we don't use any prefix indicators. We don't call that triammonium because this is an ionic compound and we can determine the ratio from the charge. The final example there has the formula NH4,2O. Again, we see ammonium ions, so the name starts with ammonium. And the O stands for the element oxygen, whose ion has the name oxide. Also be aware you can have combinations of ammonium with cationic polyatomic ions. So something like NH4NO3 would have the name ammonium nitrate. We have some examples here where ammonium has been bonded to other polyatomic ions, and we are going to try to determine the name. The first one we see there is NH4ClO, and ClO is the formula for the hypochlorite ion. So the name of this compound would be ammonium hypochlorite. Our next example is NH4BRO. BRO is the name of the hypobromite ion. So the name of this compound would be ammonium hypobromite. The next example we see there has the formula NH4CN. Cn is the polyatomic ion cyanide. So the name of this compound is ammonium cyanide. And that is the poisonous cyanide. NH4OCN is the formula for ammonium something. We are going to use our table to figure out what the name of the OCN ion is. That is cyanate. So the complete name there is ammonium cyanate. Finally, we have NH4,2SO3. We know that should start with ammonium. And SO3 is the formula for the sulfite ion. So the correct name for NH4,2SO3 is ammonium sulfite. Perhaps the hardest examples of writing ionic formulas are those that contain transition metals. And the reason that's tough is because you have to provide the Roman numeral that indicates the charge on the transition metal in that formula. So you have to do this by comparing to how many of the negative charges that are present. We will take a look at how to do that on the next couple of slides. A couple of points of note here. Transition metals always will have positive charge, and again, it's up to you to determine how much. The way you want to go about this is to first determine how much negative charge is there. You should always be able to determine by what ion is there and how many of those ions are there, the total amount of negative charge. Then you ask yourself, how many metal atoms are there? The charge on the metal atoms has to be the total negative charge divided by the number of metal atoms, because that will tell you the charge on the metal atoms sufficient enough to cancel out all of that negative charge. Then when you write the name, you have to indicate that charge in the with a Roman numeral in the middle of that name. Here we have some examples of writing these ionic formulas from Here we have some examples of naming ionic compounds from formulas when they contain transition metals. Our first example is the formula FeCl3. So, like I said, when we approach these, one of the first things we're going to try to do is figure out exactly how much negative charge there is. We know from our investigation of the periodic table and valency of the different elements that chlorines typically form 1- ions. If there are 3 of them there, that means there is a total of 3 minus charge. There are 3 negative charges, or there's -3 charge that needs to be balanced out by our metal atoms. The other piece of information we look at is how many metal atoms are there. So there's only 1 iron there indicated by the symbol and no subscript. So that means that 1 iron atom must balance out the entire -3 charge. Therefore, that 1 iron atom must have +3 charge. And the name of this compound would then be iron 3 chloride. The next example we have is TiO2. We know that oxygen typically forms 2- ions. Having 2 of them in the formula means there is a total of 4 negative charge in that needs to be balanced out by our metal atom. We see that there is 1 and 1 only titanium atom in this formula, so the 1 titanium atom needs to balance out the 4 negative charge. That means that is a 4 positive charge titanium atom. 4 has the Roman numeral IV, there. Oxide is the end of the name. Titanium 4 oxide is the name of TiO2. The next example we see is the formula PbSO4. Now we may notice Pb is the symbol for lead, and lead is not one of our transition metals, but lead, because of its distance down in the periodic table can often form either +2 or +4 ions, so we always have to provide a Roman numeral when we're naming lead ionic compounds. So we look for how much negative charge is there. We see the ion, as this case, is one of our polyatomic ions, SO4. SO4 carries a 2- charge. The sulfate ion carries a 2- charge, and there is only one sulfate ion there. So the one lead atom has to balance out 2 negative charge, so this will be lead 2 sulfate. Our next example there says Fe2O3 is the formula that we want to name. This time, we again will figure out how much negative charge is there. If oxygen likes to form 2- ions, and there are 3 of them, that means there is a total of 6- charge that needs to be balanced out in this formula for this compound. Now, however, we see that there are 2 iron atoms. If there are 2 iron atoms, each of the iron atoms only has to balance out 3 of the negative charge. So the correct name for Fe2O3 is iron 3 oxide, because each of the iron atoms must have a +3 charge. The next example we see there is AuNO3. Au is the element symbol for gold. We see there is one gold ion, one nitrate ion. If we check the polyatomic ion chart, we find that NO3 is the formula for nitrate, and that nitrate has a 1- charge, and since there is only one gold atom that needs to balance out a 1- charge, that is gold 1 nitrate. Our final example here is Cu2SO43, and this is a good amalgamation of all of kind of a harder example here. We would look for SO4 first to figure out that SO4 typically comes with a 2- charge. There are 3 of these sulfate ions here, so there's a total of 6- charge that needs to be balanced out. We've got 2 copper ions to do the job, so they only need to balance out 3 apiece. So our copper ions will need to be a +3, so the name of this compound is therefore copper 3 sulfate. Now that we got the hard stuff out of the way, we can do the easy ones. Naming covalent compounds is a lot easier than naming ionic compounds because you don't have to figure out any charges. You just have to remember a list of numerical prefixes. There are no common charges in covalent compounds, so we have to indicate exactly how many atoms are there with our naming system. To do this, we always write the name of the first element in the compound first. If there is more than one of them, you have to add a prefix to indicate that number. Note there, if there is only one of the first element, we don't use the prefix mono on the first element. We only use di and higher on the first element. On the second element, we always use a prefix, including mono if we have to include how many of that element are there. We have our naming covalent formulas examples here. The first example we see is the formula P4S5. So the first element, P, is phosphorus, so the name of this compound would be tetra, because there's 4 of them, phosphorus. Penta, and S stands for sulfur, which we will change to sulfide. Tetraphosphorus pentasulfide. The next example we see is SeF6. Since there is only one selenium atom, and Se is the formula for selenium, we won't say monoselenium, we will just say selenium. And then F6 is going to be hexa fluoride. In the next example, we see the formula Si2Br6. That is all nonmetals, so that is a covalent compound. We have to use prefixes to indicate how many atoms are there. This would be disilicon hexabromide. Our next one there, perhaps you may already recognize this one, but now maybe the name makes the most sense. We don't say monocarbon, we just say carbon. And we know that O2 can now be named dioxide. So CO2 certainly stands for carbon dioxide. The next one we see is SCl4, S being the symbol for sulfur. We won't call it monosulfur, we just call it sulfur. To indicate 4 chlorines, we are going to call it tetrachloride. On the next one, we see only 1 carbon, so carbon. 4 hydrogens will be tetrahydride. Be aware, this is a really common compound with a very common name. This is the formula for methane. It's not typically called carbon tetrahydride. The next formula we see there is B2Si. So this would be diboron. B is the symbol for boron. Diboron mono silicide. Silicon is kind of a hard one to end in IDE. The last one we see there is NF3. We will write the word nitrogen because N is the symbol for nitrogen. We won't include mono when it's only 1 on the starting element. And tri indicates there are 3 fluorines there. Trifluoride is the nitrogen trifluoride is the correct name for NF3. Now that we've taken a look at how to take a formula and give the correct name, we're going to do that in reverse. We're going to take names and write formulas from them. First, we're going to look at ionic compounds. When we're writing formulas from ionic compounds, we want to be able to determine the ratio of cations to anions that will give a balanced or neutral charge. We're going to write the symbol of the cation followed by the anion with the number of each indicated in the subscript position. Just writing a standard chemical formula. Ones are never written in chemical formulas. To indicate more than 1 polyatomic ion, we put parentheses around its formula and indicate the number of those polyatomic ions with a subscript outside of the parentheses. We'll take a look at some examples on the next couple of slides. So there are a few different systems for going about writing ionic formulas, and I will just stick to the one that I use because I think it's the best. It's often referred to as the crisscross method, and it's a shortcut for finding the ratio of these ions in these formulas. What you do is when you have a name, so for instance, I don't give the name here, but the name you would see would be iron 3 sulfate. Written down, and you would be asked to give the formula for iron 3 sulfate. And you can see here I've already listed out. I start by listing iron, and I know that this particular iron is a 3+ because there is a 3 in the Roman numerals in the name. And I write down sulfate, and I might go ahead and put some parentheses around it, and I put 2- on top. I write down the sulfate formula from the polyatomic ion chart. I put 2- with it because that's how much negative charge the sulfite ion comes from, indicated by the polyatomic ion chart. Then you crisscross those numbers to the subscript position on the opposite ion and drop the sign symbols, so drop the negative or the positive symbols, and that tells you how many of each ion you need for the correct balance. Now sometimes you can get numbers here and here that are reducible. That means they share a common divisor. If those 2 numbers are reducible, you should reduce them to give the correct formula. Never reduce anything inside of parentheses. Those polyatomic ion formulas are set. Here we have some examples. We see the first. We are asked to write the formula for calcium bromide. And calcium, we can infer from the periodic table, has a positive 2 charge. And bromine, we can infer from the periodic table, has a 1 minus charge. Performing the crisscross method, we put the 2 down here and drop the sign. We put the 1 down here and drop the sign. We don't write 1s in chemical equations, so the formula for calcium bromide is CaBr2. We see the next one, we are asked to give the name of gallium chloride, and we can see from the periodic table that gallium has a positive 3 charge, and chlorine has a 1 minus charge. If we put the 3 in front of the chlorine and the 1 in front of the gallium, the formula for that becomes GaCl3. In the next example, we have sodium hydroxide. And hydroxide is one of our polyatomic ions. It is not one of the elements. And so I will write the formula for sodium down, along with sodium's common charge, which is 1 plus. And then I will write the formula, and I may even use parentheses, for hydroxide and its charge, which is 1 minus. Putting a 1 in front of each in the subscript position and dropping the symbols gives us the formula NaOH. And traditionally, if there's only one of the polyatomic ions, a parentheses is not used. So the formula for NaOH looks like this. Our next example is beryllium hydroxide. Beryllium has a 2 positive charge, and hydroxide has a 1 minus charge. So when we put the 2 in front of the hydroxide, it will go outside of the parentheses. The 1 will be in front of the beryllium, but we don't write 1s, and so the formula for beryllium hydroxide is BeOH2. Finally, for zinc carbonate, we know that zinc has a positive 2 charge. Even though it's one of the transition metals, that's one of the ones we remember. Zinc always has a positive 2 charge. Carbonate ends in ATE, so it's probably a polyatomic ion. It has the formula CO3, and it has a 2 minus charge. If we put the 2 here and the 2 here, dropping the signs, the formula we would get would be Zn2 CO3 2. But we would notice that these 2's share a common denominator of 2, and so we would reduce them, and the formula for zinc carbonate would be ZnCO3. Finally, we will see some examples of how to write covalent formulas given a name. It's pretty simple as well. We put the first element symbol listed with the number of atoms indicated by the prefix in the subscript position. We put the element symbol listed next with the number of atoms indicated by the prefix in the next subscript position. Here we have some covalent formula writing from the names on this slide, and we are going to start with the name dinitrogen trioxide. Nitrogen has the symbol N, di means there are 2 of them. Oxygen has the symbol O, tri means there are 3 of them. Tetracarbon hexafluoride is our next example. Tetra is the prefix for 4, so there are 4 carbons. Hexa is the prefix for 6, so there are 6 fluorines, C4F6. Notice in covalent compounds, we never reduce. The prefixes give us the absolute numbers for these subscripts, and that molecule actually has 4 atoms of carbon and 6 atoms of fluorine, so we do not reduce for covalent molecules. Trinitrogen pentafluoride would be N3P5 for penta. Sulfur dibromine means there's only 1 sulfur atom and 2 bromine atoms. And phosphorus pentachloride would have the formula PCl5.